have it here?
Well, because this is government, and so I have to
I mean, like, that's not.
put in but what's really funny is that most people don't know the things that I buy. And so when I buy things like, say, a cloud chamber, they go, oh, that's cool. It comes with radar computer. But they don't know that. They go, oh, it's cloud chamber? Cool, you can have that. So, here this says, when light shines on a metal, the energy of the photon is absorbed by an electron and converted to the potential, from potential into kinetic, right? So if the photon has sufficient energy to raise the electron out of the potential well, that's what we call it, the electron will be ejected from the surface of the metal with a kinetic energy K equal to the difference between the photon's energy and the depth of the potential well. We call this the work function of the metal. So, what am I talking about? So, we kind of take a step back. When we think about, let's pretend like we can have a piece of metal that's made out of hydrogen. Pretend with me. And if a photon comes in and your electron absorbs it, it will simply jump up to a higher energy level. I'm going back to hydrogen because we already know that if we get enough energy here, that 13.6 electron volts, this electron will jump up and leave, right? But the whole deal is the kinetic energy that this thing leaves with isn't equal to the energy of the photon that came in. It isn't just HF, right? Because it's going to lose energy overcoming this hole, essentially, to get away from its proton, to get away from the nucleus. And so we call that the work function, because essentially if you apply a force over a certain distance, then you can eject these things from your material. Right? So every material will have a particular work function. It's basically the energy needed to get the electron out. Right? And then anything else left over is obviously going to be equal to your kinetic energy as it spins along. Right? So here, I think this is just, yeah, that's just a video demo sheet we're not going to get to today. Okay, so this brings up, well, it doesn't bring up, but here let's talk about the wave function. And so, well, if you guys didn't notice that, the work function has this symbol here, which I believe is a psi. That's a lowercase psi. This is an uppercase psi. That's a Greek letter. So this triad-looking thing is the symbol for the wave function. We're going to talk a little bit about the wave function today. We're not going to jump into it ever. But remember I talked about how there was a debate between, things a wave, are they a particle? And so, like I said, everything has a wave function, which we can calculate if you really wanted to. So every piece of matter, such as an electron, or energy, such as photon, can be represented by a mathematical item called a wave function. Each particle is represented by a wave function, that means position in time, such that psi times psi is the probability of finding the particle at that position of time. So you guys aren't going to be required to do the messy work of dealing with the actual wave function, but there are going to be questions that I'm going to ask about probability of finding particles. And so the whole deal is, we talked about electrons like orbiting their atoms and they have a certain shape. Well, that shape is predicted by this wave function, right? And there's a certain probability that they'll be found in one spot more than other spots, right? And so that is, if you take psi times psi, that is the probability function of what they will, of where they will be, okay? Like I said, you guys aren't going to be responsible for dealing with actual wave functions, but you will see things like graphs. They'll be like, this is the graph of a wave function. What's the probability it'll be found at this spot? And so essentially you just take whatever the function is at that spot, square it, and then that's the probability it'll be there.
Well, if it's not easy, why don't they find it themselves?
Good. So now here is Heisenberg's uncertainty principle, which I think we mentioned yesterday. So with Heisenberg's uncertainty principle, this is how it's written. And if you click there, that's a video. Like I said, I think it's a number file video about Heisenberg's uncertainty principle. Maybe it's very fast, I can't remember. But essentially, what this says is delta x times delta rho is greater than or equal to h divided by 4 pi. So hopefully you guys know that 4 is a constant, right? And you know that pi is a constant.
Yes.
H is what? Planck's constant. So this is a constant number over here. Okay. Why is the uncertainty principle like this? We don't know. Why does it have to be greater than or equal to this number? That's just how the universe seems to work. Because 4 pi has more to do with a spherical distribution, and then h has to do with the actual universe itself. But x, what does x stand for? Displacement, right?
Yeah.
And then rho stands for what? Momentum.
Yes.
Not the other rho. Come on. Of course, it's the other rho. Why would you ever be confused? So, but this should be noted that this is the displacement in the x direction. This should be technically just the momentum in the x direction. Like this is applicable for every dimension, right? And so you could write them all together as just one big formula, but this still applies. And so what this means, go back, is that you can only be very specific about one thing. The more specifically you know the position, the less specifically you know its momentum. Now here's the deal. If this was something like an electron, for example, we would know its mass. So in terms of the momentum, we're really only dealing with the velocity. Does that make sense? So how does this work, like physically? Well, if you think about the relationship between like a car and an electron, it kind of makes sense. If I have a car driving down the road, you see it driving right there. If I take a picture of that car, I'll know exactly where it is, right? I could also have an electron, theoretically, moving. I could also take a picture of it. Let's assume that I can physically do that. If you could do that, in both cases, you would know exactly where that object was at a specific moment in time, right? But taking just one picture of that car, does that tell you how fast it's moving? No. So essentially, you would know this, the x position, absolutely down to a certainty. So there would be no delta here, but your momentum would be infinite because we have literally no idea what it is. Does that make sense? Now, where the analogy breaks down is that if you took 2 pictures of your car, and you knew the time between them, you could measure the distance and go, okay, well, picture 1 was this far, picture 2 was that far. That's our motion diagrams that you learned at the beginning of Physics 1. So from that information, we could know its exact position and its velocity, therefore knowing its momentum if we knew what the object was, like our car. What happens if we try that with an electron? Well, it turns out it doesn't work. Well, yeah, because what happens is, what you guys have to realize is that in order for us to say, take a picture of an electron, well, a picture, a photograph is light coming into our camera. Well, that light has to come from somewhere.
Oh, so like, that's what it is.
Yeah. And so, like, let's say that the electron, for some reason, is giving off light, so we can actually take this picture. Well, if it's giving off light, it's going to change its energy. Or if we say shine a light on it, well then, like you say, take a flash when you take a picture, that light will come in and hit the electron, and let's say it perfectly reflects, you can actually take this picture. Well, now that the light hit the electron, when you go to take your next picture, you've given it energy, and you've pushed it, and it's going to be going in some random direction now. So you can take 100 pictures, but every time you take a picture, you're going to change its momentum, and you're going to change its position where it was. So literally, like, the more precisely you try to know one thing, the less precisely you're going to know something else.
I guess we just have to like draw it. Draw 3 bodies. Come on, why don't they just draw 3 body diagram? So easy.
It's a little different down that level.
When you're using this Jenkins said full on diagrams, so for my problem. Yeah.
So hopefully that kind of helps explain why the uncertainty principle exists. Because like if you, again, take that problem up to your car and like, okay, I take a picture of it, even if you use a flash, technically the light is hitting the car, but it's not going to move your car, right? Need a bit more light. Okay, so wave function properties. So I believe this link here is to a web page. Yes.
Oh, that's a very cool website.
This is the hyperphysics textbook. I'm not going to go over this. Essentially here, this talks about probability. This gets into it. So like, if you're like, oh, the wave function allows energy calculations via the Schrodinger equation. Well, what is that? You know, if I click on that,
There it is.
but that's not the Schrodinger equation.
What?
I mean, it's essentially this thing here. So you'll notice, like, if you've taken some calculus, you might notice, well, maybe not. This kind of looks like what here?
Oh, it's a relative.
Kind of looks like a derivative, except this is a partial derivative.
That's crazy.
So it's not something that you typically learn until like calculus 3 or calculus, not calculus. Because after you take calculus 1, 2, and 3, then you end up doing differential equations, partial differential equations, and that's where these things are hanging out. So what I'm trying to say here is there's a reason why we're not going to get too far into this, but go, feel free to click on that and see what happens. So remember, psi is our symbol, Greek letter, for wave function, so it contains all the measurable information about a particle. That's the whole point of the wave function. Psi times psi sum over all space equals 1. And the reason why it equals 1 is because there's only, we're looking at, say, electron, there's only one electron. So if you look at the probability of finding it, well, over all of space, it has to exist somewhere. Now, there's some spots in space that are much more likely than everywhere else. But essentially, the wave function is for the entirety of the universe, finding this one particular electron. Psi is continuous, right? So if you know things about math, what a continuous function is. It allows energy calculations via the Schrodinger equation, which we're not going to deal with. Psi establishes the probability distribution in 3 dimensions. So it should be noted that you don't just feed into this thing just its x position. You have to feed into it for, like, say, a electron, its x, y, and z position, and the time that you start. But if you kind of take that out, like for instance, if you went to a hydrogen atom, you'd have to feed in the x, y, and z position of both the electron and the proton. So this wave function would almost immediately become something of 7 variables. And so if you think about like an actual molecule, like say a cholesterol molecule, like how many atoms and electrons are in that thing? So for every single electron or nuclei, you end up essentially getting 3 more variables. Psi permits the calculation of the effective average value of a given variable, and psi for a free particle is a sine wave, right? So if it's just off by itself, it's a sine wave, implying a precisely determined momentum and a totally uncertain position. Because that means we can find, let's say it's kinetic energy, but we have literally no idea where they go. So the wave equation is an important partial differential equation that describes the propagation of waves with speed v. So here, this is our wave function here. And essentially, this upside down triangle is not a mistake. It's not a delta. It's called the gradient symbol. It's not a Greek letter, actually. And what the gradient symbol means is if you have a function, it means take the partial derivative of this function with respect to, like, say, x, y, and z. And so here, and that should typically equal, if you did the gradient, you would do 1 over v squared is the partial derivative of psi times this. Like, I know most of y'all have no idea what I'm talking about. But I'm trying to explain something here. Like, if you take modern physics as a class, essentially this is the whole class. Like, learning this equation, learning how to solve this equation by hand. Now, in reality, you're never going to solve this thing by hand, but if you can't solve it by hand, there's going to be no way you can program a computer to solve it. So this is one-dimensional wave equation.
So I'm not getting any further into that.
The wave function is used inside of our Schrodinger equation. The Schrodinger equation plays the role of Newton's laws in the conservation of energy in classical mechanics. So literally in quantum mechanics, we have the Schrodinger equation, which basically handles Newton's laws and our conservation laws, all wrapped into one. It's a very nice equation. It predicts the future behavior of a dynamic system. So basically, if you can feed in stuff into the Schrodinger equation, it can predict sort of where things are going to be later. But again, the problem is it predicts analytically and precisely the probability of events or an outcome. The detailed outcome depends on chance, but given a large number of events, the Schrodinger equation will predict the distribution of results. So it's a big probability function. And it can't predict exactly what's going to happen for like one particular atom or electron. But, given, we don't typically deal with one electron in our circuit, we're dealing with quadrillions of them. It's pretty good. Here are a couple of simulations. This one is probably the best, but almost nothing can run it other than a straight up Windows machine. This is a Java simulation. And so like here, this is a hydrogen atom viewer. And so this is real orbitals in chemistry as predicted by the Schrodinger equation. And so here you'll notice it says like n equals 4. And then it disappears. So if we're looking at this guy here, we can change it, so we can say, hey, n equals 1. So this is like your hydrogen atom, right? N equals 2, n equals 3, n equals 4. Notice that like nothing is happening here because I'm not giving it any protons. So here, 1 proton. So like this is like your f orbital, like your p orbital, your d orbital. So notice the s's all look spherical. But this is actually a 3-dimensional view. So when I say this is the best one here, like it's the best one, but again, like you're not going to be able to pull this up on your phone. But then there's the PhET simulation, which is Java, which you probably still can't pull up on your phone, but it works on most devices. Okay, special relativity. Unfortunately, we don't spend much time on special relativity. So let me break it down here. So first of all, back in 1905, a dude named Albert Einstein wrote not 1, not 2, but actually 5 different papers that were published. And it said that he probably could have gotten a Nobel Prize for each one of these 5 papers. Problem is, you can only get 1 Nobel Prize per year in physics, and he published all 5 in the same year. So the one he actually got the Nobel Prize for is stuff you probably have never heard of. Like, I believe it was on Brownian motion, but he published other papers that year. And one of the papers he published was on special relativity. It took him another 10 years to publish his paper on general relativity. He didn't publish that until 1950. Now, basically, special relativity and general relativity are talking about the same thing, relativity. But special relativity is basically relativity, but no acceleration. And then it took him another 10 years to figure out how to deal with accelerating things with general relativity. And one of the things that was predicted by by general relativity is the fact that gravity has a speed to it. which we just kind of think like, gravity just pulls you down. Gravity actually travels at the speed of light. And so the example that's typically given is like if the sun was to suddenly just disappear. I don't mean like collapse or explode, I mean just gone. What's weird to think is that like the light coming from the sun, it takes about 8 minutes to get here. So it's weird to think that if the sun just disappeared right now, we would still see light for another 8 minutes. What's funny about that is that light is the fastest the information can travel. And so even if we had like say a satellite orbiting the sun, like right close to it, and it saw the sun disappear, it could send us that message, but it would have to receive the information that the sun's not there, process it, and then send that message, which at best would be at the speed of light, so that would actually be behind the light from the sun disappearing. But what's even weirder to think about is that if the sun just disappeared, we would continue to orbit a sun that's not there for another 8 minutes. Because that's what was predicted by general relativity, is that the ripple of gravity through the fabric of space-time just would take 8 minutes to get here. And so we would continue to orbit nothing. Then once that gets there, well, then we would just go off in a straight line at a constant speed and go out and freeze to death.
Very nice.
Kind of made this up. But special relativity is basically just looking at how things are all relative. And by things being relative, I'm talking about like time is relative, the length, height, width are all relative to how fast you are going. So literally, the faster you go, the skinnier you are in the direction you're traveling. Now, for the speeds that we typically travel, it's not very fast at all. And there's not much length contraction in that case. But it's one of those things that relativity is used by scientists in looking at events in the universe to determine what is true and unchanging. That's one of the things that we scientists have been trying to deal with for so long. Is like, okay, what's constant? And when you think about things, let's not even take into account special relativity. If you just think about, say, like your height. Is your height constant? No. No, like not at all. And you can be like, well, it's basically constant throughout the day. Yeah, but except it's not. Like if you measure your height, like when you're just wake up in the morning, let's assume that you lay flat on your back. Actually, if you stand up all day, like gravity compresses you a little bit, and you're actually like slightly shorter in the evening than you are in the morning. Yeah. Now you can do a very, like if you just measure your height here versus measuring your height when you're laying on the floor, it'll be slightly different just because of that. But the whole deal is what is true from one perspective is not necessarily true from all perspectives. So that's one of the things you learned last year, hopefully, about like speed, where they ask you questions like, okay, cars traveling down the road going 60 miles an hour, there's another car traveling this way going 60 miles an hour. But from your perspective in the car, how fast is that other car going? It's going like 120 if you're like stationary. But in that case, the road is moving backwards at like 60. So when it's one of those things, it seems weird, but I know, especially if y'all have participated in, extracurricular activities where you have to get on a bus and go do things. You ever been one of those places where you're at a band competition or whatever, and there's like 400 buses,
Yeah.
and they're like, okay, get on the bus, and you all get on the bus, and you start moving, but like all of the other buses next to you aren't, and it starts to feel like they're moving and you're not, and you're like, what's going on? It's all relative.
I don't think I recall that feeling.
So the whole deal here is with relativity, we're trying to figure out what is not relative, essentially. Like, what is constant? And one of the only constants we seem to come up with is the speed of light. The speed of light, like Planck's constant. These are things that we keep coming back to that seem to be true in all perspectives. And that's one of the biggest things about special relativity, is that when you look at it from different non-accelerating perspectives, remember this has nothing to do with acceleration, the speed of light is always constant, and the distance between the two objects appears to be constant. And so that's one of those things that, like, they say, you know, if you're traveling, like say in a train or a plane or whatever, let's say 100 miles an hour. If I take a ball and I throw it forward, like inside the plane, well, the ball's actual speed compared to the Earth is the speed of the plane plus, let's say I threw it at 10 miles an hour. Well, now it's going 110 forward. Does that make sense? But inside the plane, it's just going to 10 relative to you, right? But what's interesting is if you have a flashlight and you're in the same plane and you turn on the flashlight, the light comes out going the speed of light, not the speed of light plus 100. It's always going its speed. And that's one of the biggest things about special relativity is that we're trying to figure out what's constant and what's not. And it can be very difficult to understand. And there's this video series that Metaphysics put together about special relativity. I'm probably actually going to play this first video here, which I don't normally do.
Writing's not that easy, but it's great.
Nobody cares, Grammarly. So first of all, hopefully you are familiar with metaphysics from Ms. Jenkins' class. But
We watched Vsauce last year.
maybe, but
We watched like 2 videos of it.
Vsauce, Vsauce actually has a really good video about time, and it will mess with your head.
Where are all your fingers?
So here, what metaphysics has done is they took a topic that's actually pretty difficult to understand, and they broke it down, but it's actually broken down through a series of videos. And one of the biggest things that he talks about, this is just an introduction to the videos. One of the biggest things that he talks about, and the reason why I'm leaving up to videos is because I'm essentially not testing you over this. He talks about how Einstein, you know, everybody is like, well, how am I supposed to learn this when it was so difficult for a genius like Albert Einstein to learn? Well, one of the biggest things that he talks about in here is that, like, Albert Einstein was a genius and he did that, but the reason why it was so remarkable for him to do it is because he essentially climbed a mountain of the steepest face that no one had ever climbed before. But once a mountain has been climbed like that, you find that there are other ways to get up there. And you don't have to go the route he went. Okay, now he went up the hardest way to figure this out. But it is the most solid logic-wise. Okay? So it's one of those things that, like, if you try to just do what Einstein did, it's going to be very difficult for you. And I don't recommend doing that. Because you're going to get frustrated and be like, well, I'm just an idiot. It's like, no, there are other ways to get to the top. You don't have to go up a vertical cliff, right? Like, if there's an escalator on the other side, like, why not just use the escalator? Like, yeah, if you want to show that you're a man or whatever, this stupid crap. Like, well, I'm going to do it this way. Yeah, okay, fine, do it. But you don't have to, right? If you just want to get up there and look, go, oh, look, this is a nice view. There's other ways.
Hi, this is Henry, and this is the first in a series of videos about special relativity. This is definitely not an academic course, but it's going to be a more in-depth and developed exploration of a single topic than a typical standalone minute physics video. I've been greatly inspired and heckled to do this by my friend Grant Sanderson of 3 Blue 1 Brown, who's set the standard for this kind of thing with his excellent series on calculus and linear algebra. So, special relativity. Special relativity is one of the most popularly famous ideas in physics. It's the thing that Einstein figured out about the speed of light and space and time and E equals mc squared. It changed our understanding of the universe, and its core ideas are accessible in principle to anyone who understands some basic algebra and geometry. You don't even need to know calculus. And yet, in spite of this, special relativity is one of the subjects in physics that confuses the most people, and in many cases turns them away from physics altogether. I think in part this is because special relativity is not quite a big enough subject to ever get its own full class in physics departments. You might see classical mechanics, or quantum mechanics, or electromagnetism, or intro to general relativity on a course syllabus, but it's surprisingly rare to see special relativity, even though relativity is an essential building block upon which most of the rest of modern physics depends. Special relativity is typically relegated to just a few days squeezed into the beginning or end of other physics courses. However, the more important reason special relativity confuses so many people is that it's almost always introduced confusingly, with lots of complicated algebraic equations with delta x's and delta x primes and square roots, which sometimes you divide by and sometimes you multiply by, and all the while you're scrambling to figure out where in all this symbological mess is there hiding a supposedly mind-blowing insight about the fundamental nature of space and time. Special relativity doesn't have to be that way, and I think the complicated explanations have only survived this long because they're how Einstein did it. But he was a professional physicist, climbing an intellectual mountain up its steepest face, and I don't think that we should require everyone who learns about special relativity now to have to follow the same path Einstein did, especially not now that we have super beautiful and simple geometric ways of explaining it. Essentially, we figured out afterwards that there's a much easier way to climb the mountain than what Einstein did, a way that you could probably even figure out on your own, given the right prompting. And it's that fundamentally beautiful, simple, geometric way to understand space and time that I want you to leave with after watching this series of videos. If all goes well, hopefully you'll gain some intuition for what special relativity really is, why it works, why it's right, and why all those paradoxes you've probably heard about aren't paradoxical at all. They're just easy confusions to stumble into when you're attacking things with an army of square roots. This is going to require some mental effort from your end. There's a very real mathematical sense in which learning special relativity is kind of like living your entire life thinking the Earth is flat, and then learning that the Earth is actually round. A round Earth isn't actually that complicated of a thing to picture. I mean, it's just a ball. But trying to get used to that idea, to really take it in and figure out how your day-to-day experiences on this flat-seeming surface of the Earth, how they fit into this new round Earth idea, that would certainly take some mental effort. It is, though, a totally different kind of mental effort from plugging lots of numbers into complicated square root formulas, and ultimately much more worthwhile. I mean, you probably have a pretty good intuition about round Earth concepts like what happens if you just keep walking east, and what's the shape of the Earth's shadow on the moon, without having to do complicated calculations in spherical polar coordinates. In fact, we're going to take this analogy to the extreme. Just like a globe is a really useful, hands-on, visual way to explore what it means for the Earth to be round, because a globe comes with roundness built in, I've designed and had built a hands-on, space-time globe that has special relativity built in. It's not quite as simple as a globe, because special relativity is a little weirder than roundness. But the thing I like about this machined aluminum space-time globe is that it's a physical manifestation of the intuition that I hope you develop for special relativity. We're going to use it to gain a hands-on understanding of the twins paradox, length contraction and time dilation, why nothing can go faster than light, and much more. I hope to see you in the next video. And while you're waiting for the next special relativity video to come out,
That's it. You can watch this series of videos, and like I said, it's a lot easier if you have one of those space-time globes, which I do not have.